We're going to look at exponential growth and finding past values. So here is our scenario. It says the country of Wakanda has a population of 6 million in 2017. If the country has a growth rate of 2%, what will the population be in 2025? And then the second question is, what would the population have been in 2000 if that had been the steady growth rate? So we're going to address this two ways. First one we're going to do is, this is an exponential function. When we look at growth rate, we're dealing with y. Let's change that. There we go. We're going to deal with an exponential function, which has the parent function of y is equal to, even though I think small, that's better. Y is equal to, we're going to call a. A is the initial value, and then we're going to say 1 plus, we can use any for this. We're going to see rate of growth. We'll put it in green, so R is our growth rate. And I put a little subscript just saying G because it's a growth rate. It means it's going upwards. And then to the power of X. So this may look a little confusing, and it's actually very similar to an exponential function, which normally looks like this. A times B to the X. All we've done here is we've taken this B and we've broken it into a type of growth rate for an exponential function. What we've said is, in order for something to grow, 1 has to represent, 1 is 100%, so that represents the whole. So we're saying the whole always stays, so there's going to be 6 million, and it's only going to go up from there. Otherwise, it wouldn't be a growth rate, it would be a decay rate, and then a decay rate would have a negative symbol here instead of a positive symbol. But since this is growth, we're going to deal with a growth rate. They said in the question that it is a 2% growth rate. We'll put it in blue, okay? So 2% as a decimal, just like 100% as a decimal is our value of 1, 2% is 0.02. So we're going to plug that into our equation. So our equation is now going to read y is equal to, also A is our initial value. Well, the initial value of the country was 6 million. So we're going to say 6 million times 1 plus 0.02. Well, 1 plus, I can do it right here, 1 plus 0.02 is 1.02. So I'm going to put that in there, blue, 1.02. And this is all going to be to the power of x, okay? And x represents time and how long something is going to happen for, how many times this rate is going to run itself, I guess you could call it. So y will be the future population in this case, and x is time. So we'll say y equals population in this case, and x is equaling time. Okay, so in order to actually solve for our population, because they asked us what will the population be in 2025, we have to figure out how much time they're asking us. They didn't give us a specific value. All they did say is that in 2017 this was the population, so what will it be in 2025? Well, because they've given us two dates, these two dates, 2025 and 2017, we can solve for time here. So let's take 2025, that's the year they want, and subtract it from 2017 to see how much time will pass in between those two values. So when we subtract here, we're going to end up with 8. Yep, it's equal to 8. So in other words, 8 years will pass from 2017 to 2025. So our x value is going to be the number 8. So let's kind of rewrite our little, whoa, that's the wrong one. There you go. Let's go and, there we go. Let's rewrite this formula we have, which that wasn't a very good representation of it. So y now equals still our 6 million population starting rate. The growth rate is 1.02. That means it has a 2% growth rate. And time that will pass is going to be 8 years. Great. So we have this, and now we're going to try to solve it. So I'm going to bring up a calculator. So here's our calculator. I'm going to clear this. The population of the country was 6 million. Beautiful. So you can see, I don't know if you can see right here in this gray strip towards the top right of the screen, 6 million multiplied by, now I need to put a set of brackets around this, 1.02 end brackets, and then to the power, I think that's the right one, to the power of 8. It's going to be equal to according to this, we're going to have 7 million. Can I copy it? Oh, no, that's not what I wanted. Power of 8, yep, is going to equal 7 million. So can I go up and get this from here? There it is. I'm going to copy the result. Just copy this complete equation. Let's go back into here and let's edit what we have. Paste. Hey, here we go. So according to this, as long as we've done this correctly, and we can double check this, we took our 6 million with a growth rate. So here's our 6 million in red. Here's our 6 million multiplied by this bracket here, 1.02. This meant to the power of, this power of 8 should equal 7,029,956 point something. We don't really have point values of humans, so we're just going to rewrite this value as 7,029,956. Great. That is a future value. And I said in this video we're going to deal with past values. So why did I do that? I did that because I wanted to show you that that was time going forwards this 8 years. But in the second part of this question, what would the population have been in 2000? Well, that's time in reverse. How do we go about doing that? Well, we don't actually, it's a very common mistake to think that here our growth rate becomes a decay rate, and we say, oh, y is equal to a 1 minus that growth rate, which was that 0.02. 0.02 to the power of x. If you plug that in, we'd end up with y is equal to 6 million. I'm going to just write that for 6 million. And then 0.98. When we take 1 and subtract that 0.02, we'd end up with this. But that's actually incorrect. That would be a decay rate. We never said this was a decay rate. What we're going to do is we're just going to do reverse in time. And because 8, we didn't write it, it's technically a positive value when we go forward. If we want to go back in time, we would have a negative value. So I'm going to shrink this a little. Shrink everything here. Be nice at this. It will not allow me to do so. Oh, but I can just drag down the screen. Hey, I didn't know that. That's great. I learned something. So what do we mean by that? Well, they're asking for the year 2000, and the population of 6 million was in 2017. So this one's a little easier to figure out. How many years ago was that? Well, that would be 17 years ago. And how do we represent going back in time? We would just say x is equal to negative 17. So we set up the exact same formula. Y is equal to 6 million. I'll write all those zeros. Still the growth rate of 1.02, but this time it's to the power of negative 17, a different value. Okay, so let's take a look at this. What would this be? Let's go to our handy calculator. Look at this. So, sorry, I jumped out of there. I'm looking at this number, and as you can tell, I paused for a very long time because I thought I made a major error. What this actually means with this decimal here and then the e to 39 on the left, it means it's a really, really small value, less than 1, which... how can the population be less than 1 at some time? And what I discovered is this app is kind of broken. It can't do negative exponents. So I went to trusty old Desmos, and I put in 6 million to the power of 1.02, and then I put in the values here of where they intersect the line. So I double-checked on our first one when x equals 8, and x equals 8 at 7 million. Did I have 7 million? Yeah, that's right. I have 7 million. I'm struggling here. Get it. This number is incorrect. No, sorry. 7,029,956. Which, sorry, I had trouble reading that number. 7,029,000. All right, that was our correct number before. And then I went and put in x at negative 17, and x at negative 17 is, here's our value, 4,284,000, went away, 284,975. So we're going to put that in, 4 million. In fact, it'd be really nice if I could control center and just bring up value should be able to bring this into here. I don't remember how to do this now. There it is. I want the decimals app. And on the side, great. There we go, now I can see my number, great. So now they've put it in, it is 4,284,975. We don't have decimals of a person. So this would represent the population in Wakanda 17 years ago. So we don't make it a decay rate, it's still a growth rate, we just use a negative exponent value to calculate backwards in time. Let's get rid of that. No, that's not, there you go. Okay.